Hi, everybody. This is your sickly teacher, hoping to wrap up section 14.6. Um, okay, 14.6, talking about the Jacobian determinant. In class on Thursday, we had gotten into, well, technically example number two, but what my thought was on this problem was to dive in and try to attack this problem in as sensible a way as we could without necessarily defining the Jacobian determinant yet. Because I think it gives us a better appreciation for what the Jacobian's trying to do or what it does. So we were looking at this integral, 3x plus 2y over x plus 4y, and realizing that since the x's and y's were all coupled up in the numerator and denominator, it would have been really, really hard to integrate with respect to x or with respect to y. Um, yeah, and so making a change of variables, just like a u substitution type problem, uh, would be a good way to go. So the way that we decided to tackle it was make the top u and the bottom v. And so we set those out. We took derivatives of u and v with respect to x and y. Um, Basically, we're looking at the differentials here, the total differential. So u becomes du is partial u partial x times dx, partial u partial y dy. So du is 3 dx plus 2 dy, and dv ended up being dx plus 4 dy. And we drew this parallelogram out in space because if dx and dy were kind of our standard basis vectors, I hat and j hat, du and dv would look like this because they are linear combinations of dx and dy. And areas in this new space would be scaled by 10. We related that back to the cross product and taking determinants, taking this 2 by 2 determinant of this is our first vector, this is our second vector, taking this 2 by 2 determinant gives us 10. And yeah, when we take cross products, the length of our cross product vector is the area of the parallelogram spanned out by the two vectors that you're starting off with. Um, and so, yeah, in this way, we found that there was a scale factor of 10. And so, if we were going to make those areas equal, we would need to multiply 10 times dy dx to get du dv. And since we have the objective of changing this from a double integral with x's and y's into a double integral with u's and v's, what ends up showing up here as the Jacobian determinant ends up being 1/10 because, we could divide both sides of this equation by 10 and get dy dx is equal to 1/10 du dv. And so, yeah, this factor of 1/10 shows up here. And after doing that and changing the bounds to appropriately match what's in here, to come up with these boundary considerations, when x is equal to 0, that would mean that u is equal to 2y, v is equal to 4y, and that v is equal to 2u. And so, yeah, there would be some considerations to be made for, in what order we want to integrate. But since this is the shape that we're integrating over, um, yeah, I mean, integrating with the lower function as v equals 1/3 u, which happens when y is equal to 0, up to the function v is equal to 2u as the upper bound, That happens when x is equal to 0. And we get u is equal to 2 because 3x plus 2y is equal to u, and that's coming out from our third equation that kind of used to be the hypotenuse of a right triangle, but now it's forming this right-hand boundary in the transform space. So yeah, after having done that change of variable and setting up these bounds to appropriately capture this, actually solving the integral is not too bad, since we're integrating with respect to v first. Antiderivative of 1 over v would be the natural log of v, and u's just coming along for the ride. Yeah. So things out. We get to this stage. This looks pretty gross initially, but since we've got natural log of 2u over 1/3 u, those actually, you can divide those and get 6. And so this second part just becomes the natural log of 6, and you can throw that out front. And then you're just taking the integral of u to u. You can get that there and get natural log of 6 over 5. So this is one way to do it. It's the way that we had discussed last Thursday. But doing it this way did not require the use of a Jacobian determinant, but it did give us a visual sense of, as we change variables here, it looks like our areas are expanding, and therefore we need to counteract that expanding area with this factor of 1/10 to make sure that things stay equal. And so, yeah, we're going to run through this problem again using the Jacobian determinant, and you're going to see that there are definitely connections there. Basically, when you're doing the Jacobian determinant, and I think that we even touched on this on Thursday, we're going to have to solve this system of equations for x and y rather than u and v. In this case, it seems, it was really easy to just work with these equations, solve for u and v, because that was just the numerator, that was just the denominator, and we didn't have to do any extra solving. But to do the Jacobian determinant, we're going to need to solve those for x and y and take partial derivatives of x with respect to y and x with respect to u and v, or y with respect to u and y with respect to v. Anyways, we're going to see this another way. It's going to be the way that is generalizable and doesn't maybe require us to think as critically about areas changing. It's just going to be more like, oh, hey, here's a nice formula and we can just plug things in. Okay. Actually, yeah, let's go back to this one. Okay. So, this notation with partial xy over partial xv and the absolute value signs along each side, that part is the Jacobian determinant. And because we have those absolute value signs, we are going to want this always to be positive. As a scale factor to translate between x and y coordinates into u and v coordinates. In order to calculate the Jacobian, we are going to take 4 partial derivatives, and those are going to be entries in a matrix, in a 2x2 matrix. The top row of the matrix is the gradient of x with respect to u and v, and the bottom row is the gradient of y with respect to u and v. And so it's this cluster of partial derivatives is what we end up calculating to calculate the scale factor from x and y into u and v. Example number 1 is to use a Jacobian to derive the formulation of double integrals in polar coordinates. This is one of the instances where we have x and y already solved for us. Polar coordinates, we would have x is equal to r cosine, r cosine theta, and y is equal to r sine theta. And so, to calculate the Jacobian, we'd be taking the determinant of a matrix where we've got partial x, partial r, partial x, partial theta. So that's the gradient of x on the top, the gradient of y on the bottom, partial y, partial r, partial y, partial theta. And so, if we look at that x equation and we take a derivative with respect to r, we'd just be left with cosine. And then if we take the derivative of that x equation with respect to theta, we would have negative r sine theta. We take the derivative of y with respect to r, we would have sine theta. And if we took the derivative with respect to theta, we would have r cosine theta. So that's our Jacobian determinant in this case. I mean, we've got to solve it out. We do main diagonal minus the off diagonal, and we're looking at both of those products. So we've got r cosine squared theta for that first one, and then we would be subtracting off minus r sine squared theta. And so in the end, we get r cosine squared theta plus r sine squared theta. And since we know our Pythagorean identity, we can factor out an r and get cosine squared plus sine squared. And that just equals r. So that whenever we do a translation between dy dx into polar coordinates, that's r dr d theta, just like we expect. So that factor of r gets thrown in there in that change of variables. Here is our second look at example 2. And I've got the stuff already written out. We're going to take a high level view of this. Okay, so same thing as before. We decide on a helpful transformation. With Jacobians, I feel like there's going to be, you're probably going to be doing a Jacobian for one of two reasons. One of them, it might be making the integrand into an easier function. So right now, it would not be easy to take the integral of this function because we've got x's and y's on top and bottom of this fraction, and they're just not easy to uncouple. It's the thing that Symbolab just kind of quits and says, no, I don't want to do it. So making the integram look better is a good reason to use a Jacobian. There's also going to be reasons that maybe this will be more like the one that we do on our activity, but changing the variable so that the region of integration looks better. That's another reason to do it too. Okay, so first step, you decide on a helpful transformation. And so these two equations give us a relationship between x, y, and u and v. And in order to determine the Jacobian, we want to solve those equations for x and y. So yeah, solving those equations for x and y. I think in class on Thursday, we used more of a substitution type of strategy. Here, we're using maybe more of an elimination type of strategy where we're using these, but maybe we multiply the second equation by -3, add those together to get rid of the x's. Maybe multiply this equation by -2, so that when we add these two equations together, the y's drop out and we're just left with x. So solving for x and solving for y is a thing, and then we can take those partial derivatives and get 1/10 that way to to find that scale factor between x, y, and uv. This again is just a diagram of the two regions. When you're using a Jacobian determinant like this, it seems like the transformation is backwards from the way that you might initially imagine it, because what we're doing is we're changing from xy coordinates into uv coordinates, but the way that we're calculating this Jacobian determinant with x and y on top and u and v on bottom really does correspond to kind of u and v coordinates being transformed into x and y coordinates. But yeah, after having calculated the Jacobian and having that scale factor in hand, you would work on the boundaries, get those boundaries in order just like we did before, and then solve the rest of it out like normal. Cool. There are not a ton of examples in this section. So right now we're moving on to Jacobians for a three-dimensional version where we're, moving from 3 variables to another 3 variables. So now it's x, y, z into u, v, w. The top row again is the gradient of x with respect to the other 3 variables that you're transforming into. Gradient of y on that second row, gradient of z on that third row. So that's the organizing principle that I would keep in mind when you're trying to write down which things belong in the Jacobian matrix. Goodness, my mouse wheel is awful. I can scroll down, but it bounces back and forth. Cool. So yeah, that scale factor. Example number 3 is here to derive the change of variable between x, y, and z and spherical coordinates. And yeah, hopefully this doesn't look completely foreign because we've talked about spherical coordinates. Yeah, x is equal to rho sine phi cosine theta. The rho sine phi part is little r, the radius of the circle, whereas rho is the radius of the sphere. So yeah, this is still r cosine theta, r sine theta, rho cosine phi. We've yeah, we've seen how these were derived. And to get the change of variables from x, y, and z into rho, cosine, and phi, you could take this 3x3 Jacobian determinant and calculate 9 different little partial derivatives. And after you take the determinant of this, I mean, this 3x3 determinant becomes 3 2x2 determinants that get calculated this way. And in the end, eventually, you get to negative rho squared sine phi, which is the rho sine phi thing that we expect to see in spherical coordinates. But like I said earlier, when we are converting between coordinate systems and working with integrals like this, we're taking the absolute value of the Jacobian just so that we get the scale factor that we need to translate between one coordinate system and the other. So we're taking the absolute value, and that's why we see rho sine phi instead of this negative sign in there as well. Cool. So yeah, that's that. The last one, example number 4, is an example where we're doing the transformation primarily because it'll make the region of integration look better. Right now, we are integrating over this parallelepiped, which you can see is slanted. It's, really close to the y-axis here in the bottom, but it's slanted away from the z-axis as you go up. And so, especially if you're thinking about integrating with respect to z first, this z surface is not directly over this z surface. And as you integrated along, you would have different upper and lower bounds. Like I would expect for a while for my upper bound to be this top surface and my lower bound to be this slanty side. And then after doing that for a while, maybe there would be a small region where I'm going all the way from the upper bound to the edge of this lower bound down here, all the way on the XY plane. And then if you continued integrating, you'd probably be down here and working with a slanty edge. Because this region of integration is slanted, you could very easily be having to do 3 integrals because your upper and lower bounds keep changing. Maybe that could be alleviated if, well, it looks like the top and the bottom are parallel. So possibly integrating with respect to x first or with respect to y first might get you might get you a shape where the top and bottom bounds aren't changing as much. But this is an occasion for us to illustrate that, hey, working with a Jacobian can actually make solving this integral easier because we won't need to set it up as 3 separate integrals where the top and the bottom boundaries change. If we change this parallelepiped to be a rectangular prism, the boundaries are going to be really, really simple. So one of the things that makes this possible is that our functions of x and z have the same, scale factor, I guess. Yeah, we're multiplying by the same thing here. We've got 3x is equal to z and 3x is equal to z plus 3. That 3x equal to z being common to both of those is going to allow us to make a change of variable to take that from a slanty kind of thing into an upright kind of thing. And we do that by assigning u as 3x minus z. That means that the slanty faces of the parallelepiped can then be written as u equals 0 and u equals 3. If you subtracted z from both sides, you would get, that. And the other ones actually look pretty nice compared to, we've got constant functions here for these two planes. We've got constant functions here for those two planes. And so, yeah, we can go down here and look at the details. But what that'll allow us to do is make this kind of a change of variables. We've got u is equal to 3x minus z. V is equal to z over 2. W is equal to y over 3. Those, especially for v is equal to z over 2 and w is equal to y over 3, is that really necessary to change those two? Would it have been just as easy possibly to, leave x and y as they were? Or sorry, z and y as they were? Maybe. But yeah, dividing by 2 here and dividing by 3 here, I think makes this part slightly nicer. So instead of having divided by 2 here and divided by 3 here, when we translate things into u's and v's and w's, that equation, or yeah, that expression becomes simpler and just having u over 2 plus w. So yeah, if this is our change of variables, we can solve these for x, y, and z, our original variables, and then we can calculate Jacobian determinants. There's our 9 partial derivatives. Really, this one's kind of boring because we've got some boring functions to work with. In the end, though, you get a determinant of -2. We're taking the absolute value of that determinant, so it's a 2, and the scale factor works out like this, and the bounds on the integrals are really easy, so that it is not too hard to get from here to 15. So yeah, using a change of variables to make the region of integration nicer is a thing. And we're going to do something very similar to this on our activity. All right, so that's it for this little wrap up of section 14.6, looking at Jacobian determinants. I'm going to record stuff for the activity and for our homework, and I'll see you then.